Thank you very much. First of all, I have to say this was a lot of great examples that we learned in the previous talk about how big data is being used. All right, so in the next 45 minutes, I'll be talking in depth about stream processing. So my name is Kartik, and hopefully in the next 45 minutes, we'll all have some takeaways. First off, a little bit about me. I manage the Streams infrastructure group at LinkedIn, which comprises of messaging platforms like Apache Kafka, change capture platforms. Change capture is basically from data systems like we have a NoSQL database called Espresso and Oracle. So Databus is a system that we developed in-house, which captures changes from these data systems and makes them available downstream. And lastly, we have a stream processing platform that we have built at LinkedIn called Apache Samza, which is also a top-level Apache project. And we'll learn about all of these things more in depth as I talk about stream processing. Close here. All right. So prior to LinkedIn, I spent about almost 15 years at Microsoft. I spent time in different areas. Initially, it was all about servers. Then I spent some time on .NET Framework and like with web services and the workflow stack. And then in the last 5 years, I was building services. So I built the messaging platform for Microsoft, and me and my team first focused on enterprise messaging with queues and topics and kind of rich feature set. In the last 2 years, we were focused on cloud and Internet of Things style messaging with Event Hub. So with that, let me talk through our agenda. So first off, we'll do a very brief intro on stream processing. I think most of you probably already know about it, so I'll keep it brief. We'll go into some scenarios, and then I will talk about what I call the canonical architecture. This is just to set the context for how we, for the broader architecture in which stream processing plays. And then we'll do the deep dive onto stream processing itself, and which is where I'll spend most of the talk. And then we'll close. I'm going to try to go a bit fast because I know we are running a little late. All right, so real quick on this. So I think you might have seen this slide before. This is just to indicate the fact that on one end, we have like RPC style, synchronous services, which is like every web service website out there. On the other hand, we have Hadoop, Spark-like processing, which is done at a much later time frame, like possibly hours, even days after the actual work actually even happened. And then we have stream processing. So stream processing is basically everything that happens in your production environments asynchronously, right? Basically, the clients are not waiting for this processing to happen, but all of this is happening asynchronously. So this is something that has been going on for decades. We used to call it queuing and asynchronous processing. Now we call it stream processing. Feels like a much cooler term. So hey, what the heck? Cool. Let's go into some scenarios for what's motivating stream processing in today's environment. So this is a real scenario at LinkedIn. At LinkedIn, we want everyone to come into LinkedIn and see latest information about what's happening that's relevant for them, right? It could be about news in terms of the domain that you're interested in. It could be news in terms of some connections of yours who did interesting things. But we want this to show up in real time, right? We don't want it we don't want you to see news that happened like 4 hours ago or even a day ago. We want it to happen, be there immediately. And by the way, this is true for practically every system out there that you want to use at LinkedIn. We want the website to be very interactive. Security, everyone's familiar with this. Anyone with the internet property, is worried about credit cards getting stolen or getting DOSed or any such thing. One of the big things about, like if you want to secure a website is to monitor it, right? So you want to monitor how much data is getting downloaded, how many connections are being made to your sites, and you want to process all of these metrics in real time. Possibly alert on them, possibly they take some corrective action to kind of mitigate the issue. This is another kind of key example of where stream processing is very prevalent. And this, everyone's heard about this now. The Internet of Things is the cool new hot thing out there. Basically, all of us have wearables or, devices at home, sensors out there, which are all sending this, huge onslaught of data onto the cloud. And, many times, that data is processed offline, and sometimes it's, you figure out trends and so on and so forth. But a big part of the scenario is to process it as it comes, right? You want these devices, to be monitored. Sometimes you want to raise alerts, and sometimes you want to, based on some business rules, send some control events back to the devices. This is another, standard and very cool example for real-time stream processing. Great. I think we can keep going on and on this. So I think at this point, it's good enough to set the context. All right, so with that, this slide is meant to just provide like the broader architecture under which stream processing is interesting, right? This is the architecture of how things work at LinkedIn for the most part, but this is pretty much how many services out there work, right? So in the top, we have devices, clients, sensor, whatever it may be, which are talking to this thing in the cloud, and I call it the services tier, so to speak. And the services tier, turns around and typically records the information that the client is sending, right? Either records it in a distributed database. At LinkedIn, we use a database called Espresso. It's a homegrown database. Or basically, you're recording events just publishing into a messaging system like Kafka, or you might be using Kinesis or Event Hub, or whatever it is you use out there. So this is the part which I call ingestion. So you ingest into your databases, your messaging systems. And one key aspect in terms of ingestion to databases is these days we also have change capture systems. So Data Bus is a change capture system that we built at LinkedIn. And what it does is it mines the transaction logs of databases, Oracle and Espresso, and makes them available to downstream systems to consume. So it's very much like Kafka. So actually, we are also working on another version, the next version of Data Bus, which is going to be built on top of Kafka. Great. Once this data has been ingested, we want to process it. Now, the processing, there is a hard path, which is real-time processing, and you might be using Samza or your favorite framework, Storm, Spark Streaming, whatever it is. Or you might be doing it, batch processing in Hadoop and Spark. So for the most part of this talk, we are going to focus on real-time processing. But the interesting thing here is that all this processing derives some output, and this output has to be typically served back to your clients. In the case of real-time processing, you generate output incrementally, right? So in LinkedIn, for example, we push this output onto our NoSQL database. And if you're doing batch processing, typically you just produce the entire result set. So for serving that, we have some specialized databases. Like in LinkedIn, we have Voldemort read-only. There are other databases out there which basically support this concept of a bulk upload. So you upload pretty much the entire new result set. And like Voldemort basically has the ability to swap the result set without having any impact on the end user latency. And now, at the end of it, we also have the services tier, which basically merges results from your hard path and also from your cold path, so to speak, and then merges it and serves. So this is what most of you are familiar as Lambda architecture. And yes, this does exist at LinkedIn as well. But the rest of the talk, we are going to talk about how even with real-time stream processing, you can pretty much get everything that you need, and you don't need to use Lambda architecture for every application that you're going to build. All right, so with that context, I'm going to dive into stream processing. Okay, so stream processing, it's a broad area. I like to talk about 4 parts, and these are all aspects that are critical in terms of making stream processing broadly usable, and also these are all some of these aspects also have a relationship with Lambda architecture. Great. So the first one, the most important one, is scaling. And the caveat is that we all want to scale, but not like at any cost. We all have some budgets to take care of. Great. So before we talk about scaling the processing, I need to introduce you to some basics about the ingestion aspect, because I'm going to use that in the rest of the talk. So as far as ingestion, this is pretty standard, architecture for Kafka, Kinesis, Event Hub. All of them have a similar pattern, where you have the notion of a stream, which is partition. The partitions live across many, many machines. And then when you send a message to the stream, the message has to have a partition key. The key is used to, key is hashed, and we decide which partition to send the message to, and that's how it works. Another key aspect of all of the systems is time-based message retention. What this really means is that the data is sent into the system, the data will stay there for some period of time, which means you can go back and then you can reprocess the data. And this is a critical feature as well, and we'll leverage that in the slides further. All right. Now that we know that the ingestion was horizontally scalable, now let's talk about how does the processing get horizontally scalable. So each system, by the way, Samza, Storm, Spark Streaming, and others have their own mechanisms and their own kind of architecture. This reflects more about how Samza works. So you have this distributed stream. You want your processing tier to also be kind of distributed. So you deploy this onto multiple machines. And the system automatically figures out which node is going to process which set of partitions. And with that, a partition gets processed by a single machine or a single container. And that's how you horizontally scale your processing. In this example, I also explained that this Samza job or stream processing job produces output that just can be used by further processing. Typically, as far as your stream processing is concerned, you may not just have a single stage. You might have multiple stages. Like in this particular example, I have one job which merges 2 streams, stream A, stream B, and then produces some output based on it. And then we have another job which basically takes that and then does some more munging on it. So as you can see, this is very similar to how MapReduce works in Hadoop. The only difference here is that we are doing this processing on data in motion as opposed to data at rest. All right, so we talked about horizontal scaling for both ingestion and also for processing. All this is great, but this means that every time I want to scale, I keep adding machines. Well, machines don't come free. With AWS and lots of other cloud computing platforms, sure, it is easy to add machines, but that doesn't mean they come free, right? So that means that we need to be thoughtful about efficiency of our stream processing platform. So now the question is, what's the key bottleneck? Well, it turns out, at least for most of the scenarios that we have looked at, accessing data is a key bottleneck. What do I mean by that? This could be accessing adjunct data. So like to process your event, sometimes you have to look up a database. Well, that's what I call adjunct data. Or, as part of processing, you might want to generate new results, and then you might want to kind of read it back and iterate on it. That's what I call read-write data. So let's take an example of adjunct data, which is read-only data. So in LinkedIn, we show you ads, and then, every so often you click on it. Now, all these ad clicks are sent into Kafka. In this particular example, we have a processing job which reads these ad clicks, and then it looks up, which user clicked on this ad, figures out features about this user. For example, which domain does he work on, which company is he coming from, and so on and so forth. And then based on that, we try to improve our machine learning algorithms and such. And we generate new events, which are processed by, processed downstream. Now, in this particular example, the problem is that if for every ad click event, we have to go look up a remote database, well, that costs CPU because we have to serialize the data. That causes network traffic, increases the latency. It can also DOS the database. Like member database, as you can imagine, is a very important database for us at LinkedIn, and DOSing it is a problem. So now you could say that I'm going to put some caching tier on top of it, that protects the database. But then there are other issues with that, like how do you keep the cache in sync, and so on and so forth. And we have all walked down that path, and it is not trivial. Before we talk about solutions for it, I want to give another example, which is about read-write data, right? For read-write data, I just picked an example, which is not LinkedIn specific. This is regarding IoT. Like you have all these sensors sending this data into your ingestion tier. You have a processing job. Now, maybe as part of your processing, you want to update the state of the device, right? And you want to read it, you want to, and make incremental updates. So this is what I call as read-write. And here we have the same issues: latency, CPU, network. And here, at the end of the processing, you might still be generating output. Great, so how do we solve this? How do we make some of these problems go away? So what we do at LinkedIn is we have this notion, in our stream processing system, we have this notion of local state. So in the same example that we looked at, which is the ads example, here the stream processor job is reading the ad click stream. By the way, note that the ad click stream, in our case, is partitioned, again, by member ID, right? So every member in LinkedIn gets an ID, and the ad clicks is partitioned by the same ID. So the Samza job reads this, and in this particular case, looks up the member-specific information in the local, in a local database. We use an embedded local database called RocksDB. RocksDB is an open source database. It was built by Facebook. We use it extensively at LinkedIn. It scales very well. Now the question is, well, how did the member database, member information get into RocksDB, right? How did this clone get created? Well, the way we do it is, again, using data bus. So data bus uses, the transaction logs of our downstream databases, and anytime we make any update to our profile, let's say we changed, the location or the company that we work for, Databus gets that information and pushes it upstream. So with this, we are able to keep a clone of the member database locally in the job, right? By the way, there are other systems out there. DynamoDB just recently, maybe a couple months ago, released the DynamoDB streams, which does exactly the same thing as Databus. The same mechanism can be used in other systems, basically. Great, so now we have the state locally, access is fast, we don't have to go over the network, but then we just created ourselves a problem, because if the machine dies, what happens to the local state? Well, obviously, this is something that has to be solved. So the way we solve it is every time we write to our RocksDB local state, we also write to a remote store. We use a special feature of Kafka, Apache Kafka, called log compaction. With log compaction, you are able to produce this change stream into Kafka, And Kafka basically compacts the topic based on the partition key. So basically, if you update the topic, update a particular key like 10 times, Kafka makes sure that it's compacted so that it doesn't infinitely grow. So now what we have is any write that we have written to the local state is also being written durably into a remote store. And so now if a machine dies, guess what? Your cluster manager, like we use Yarn in Samza, but it could be Mesos, it could be AWS. You get a new host, and on that host, the same tasks or the same partitions get loaded. And then what you do is, before you do any more processing, you have to read up the entire state from your changelog, which is your durable remote store. And once you have read it, populated your local state, then you are back in business. Now, obviously, we have to be careful about this. Reading state from a remote database or a remote topic is expensive. It can flood the network, all of those things. So you have to make sure this only happens when the machine dies, not anytime the job gets upgraded and such. All this is great. It's good to put things in perspective. Here are some numbers that we got in terms of benchmarking Samza. So if you do a simple pass-through job, which doesn't have any local state, just reads and writes back into Kafka, then we got about 1.2 million messages per second on a single machine. So all of this is, by the way, on a single machine. Once we add local state, we got around 400,000 messages per second. By the way, these are not optimized numbers. So for every event we read, we also wrote to RocksDB. We didn't do any optimization. So this is basically 400,000 writes into your local state as well. And then as we introduce a local state with durable backup, with Kafka backup, we got around 300,000. So it scales very well and kind of works very well for us. Great. So the summary, it's great for local state. It's great for read-only, read-write data. The secret sauce to this is, you need to get data into your local state, so you need some change capture system like Databus or DynamoDB streams. And then you need to push the data back onto a durable backup, and for that you need something like Kafka log compacted topic, or you can write to DynamoDB with DynamoDB streams. Great. That covers scale. Coming to the next part, reprocessing. So what is reprocessing? Well, we all know that when we deploy new software, we can have bugs. When you have bugs, and let's say you've been processing all this event stream, you created a new bug, and now you're spewing bad output back into your system. So what do? Well, remember that all of these source systems have time-based retention, which means you can rewind your stream and then reprocess the stream. And this kind of, super critical. And sometimes it's not even a bug. Sometimes your business logic changes, and we'll give some. Actually, the next slide is about an example of changes in business logic, so to speak. So an example that we have here at LinkedIn, you can all go to LinkedIn and you can write whatever you want as your current title and your current company. You can say you work at the best company in the world, right? But in LinkedIn, we need to figure out what did you really mean by work at best company in the world. We need to infer, right? And the way we do that is that we have a bunch of asynchronous standardizers, as we call it, which is we look at the input and we figure out, okay, based on some machine learning model that I created, most likely you work on XYZ company instead of the best company in the world, right? So now, as you can imagine, our machine learning models evolve. So we come up with a smarter way of doing some standardization, either on your title, company, whatever location. So we deploy a new machine learning model. Great. So now we can process new changes, but what about existing members, right? The other 400 million members or whatever, how do we process them? Well, to do that, we have a feature called bootstrapping in Data Bus, which means that you can tell Data Bus, give me everything. And Data Bus basically starts reading from the database backups of our database systems, right? Streams the whole backup back onto the stream processor. And after you process the entire database, it seamlessly switches over to the live stream, right? So you basically start this and then sit back and wait for your processing to finish, and then you are back online. So this is, without this capability, the only way you deal with this would be, you would, in Hadoop, with Lambda architecture, you would reprocess the entire change set, and now you would have your hot path only deal with incremental updates. So this is a way for us to merge, your hot path processing and also your reprocessing when you have to do that. Of course, there are a bunch of caveats with this. First of all, stream processors are fast, which means that if you go back in time and reprocess it, you can DOS the system, right? Many companies out there are so sensitive about latency, they keep their online systems and your offline systems separate, right? They don't always run the 2,000 node Hadoop cluster, let's say, in the same place where they run their website, because Hadoop can flood the networks and then it can cause impact on your latencies. But when we do reprocessing like this, we can have a similar effect, right? Now, having said that, typically your stream processors are much smaller, because since they have to only do 10 minutes of processing in 10 minutes, the clusters are always smaller. You don't have 2,000 node stream processing clusters. So the impact can be smaller. We also have a way of controlling concurrency. Like in Samza, for example, you can change the container count, which is a way of making sure that you don't have more than X number of threads in your distributed system. You also need quotas. So if you're going to update databases online, you need quotas. Like every database or every service out there in AWS or Google, whatever, have quotas. So if you try to push more than X QPS, they're going to reject it. And then at the end of the day, though, there are some ground realities, right? Like I said, your clusters are only so big. So if you have to reprocess and the data set is like a petabyte or like hundreds of terabytes, well, you might be better off using Lambda architecture for that. Maybe those are examples where the existing proven kind of big data crunchers, built out there, Hadoop, Spark, are a better fit, right? Great. So, by the way, during all this reprocessing, does it mean that you no longer are real time when you're doing reprocessing? Well, that could be an issue. There are some ways to mitigate it. I would have gone into it, but I think I need to make forward progress because we're going to run out of time. Okay, next step is accuracy of results. This is important for stream processing. You would say that it's important for every program out there. If you can't have accuracy, then it's moot, right? But before we talk about accuracy, we need to spend a little bit of time understanding how stream processing works, right? So let's take this example. We show you ads. Sometimes you click on the ads. So there's an ad view event stream, and there's an ad click event stream. There's a processor which has to perform a simple rule, which is, if the ad got clicked within 2 minutes of the ad being shown, then it's a good ad, right? Otherwise, we showed you a bad ad, and we update our machine learning models and such offline, saying that this wasn't a good ad. So it's important that we don't make a mistake, right? Which means that if the ad click event is processed late and if there are delays in it, then the output can be wrong, right? So let's motivate this even further, because many people say that, okay, how often does it happen? How often are delays kind of real? This is an extreme example, but the motivation here is to help you kind of understand the crux. In this particular case, as you can imagine, Most services have some kind of geo-redundancy. So when you kind of log in, we redirect you to one data center, and then you're kind of operating in that data center. Now, oh, sorry, wrong button. Now, if there is any problem, we fail over. We fail over user traffic into another data center. And as you can imagine, now the add view event went to one data center. The add click went to another data center. Sure, the Kafka topics underneath are all mirrored, so all data is there in both data centers, and so your stream processor is actually processing both this add view and add click events. But now we have two problems. One is there can be late arrivals, which means the add click showed up, let's say, 10 minutes after your add view event, right? Or there can be out of order arrivals, whereby the add click shows up first, and then the add view shows up. So your stream processor has to be able to react to these things, right? There's been a lot of very cool research work happening in it in the last 10 years. Google produced a paper called Millwheel, which has a lot of these things explained in detail. I would recommend everyone who's interested to go read it. So let's talk about the solution. The solution is not straightforward, but it's not super complex either. In the case of Samza, the way we think about it is we basically have to capture all the events locally first, right? Since we can have late arrivals, when we can have out-of-order arrivals, we need to first store all the events locally. When you store it, you can obviously compress it, or you can condense it throughout the junk that you don't need, and just store what you care. So that way, the size of the local store is in control. Next, when there is a late arrival, we need to find out all the windows, because a late arrival can impact multiple windows. Because you can have sliding window, or you can have a tumbling window. So depending on what's your logic, you need to find out all the windows that were impacted, and you need to recompute the result, right, for those windows, and re-emit the results. And when you re-emit the results, you have to be careful, because it all depends on how your downstream system is going to consume it. Some systems can be idempotent. So let's say the previous count was 10, new value is 11, and you can re-emit the absolute value 11, and the downstream system is fine. But maybe the downstream system actually wants to know what was the old value and what's the delta. So that's another strategy that you need to kind of think about. And all of these things are also a problem, in Lambda architecture. So many times people think that if you had Lambda architecture, you don't have to worry about these late arrivals, because anyways you're processing it 1 hour after, or maybe a few hours after the event arrived. But that's kind of true. However, we have to deal with the edges, right? Let's say you're processing every 1 hour. Well, some sessions start before that 1 hour and after that 1 hour. So you don't have all the events. You also have not just delays, but out-of-order processing issues as well. Because remember, the same pipeline is also feeding Hadoop, right? So whatever are the delays in the pipeline show up in Hadoop. So you have the same problems in Lambda architecture. And if you need accuracy, you need to fix. You need to have other mechanisms to kind of help you there. Okay, so that goes through most of the hard stuff. To make stream processing really ubiquitous, we need to have these hard things kind of solved and make it available to developers which are like at a higher, so that the developers don't have to deal with these low-level issues. So first of all, you need the platform to help with the windowing, joins, and produce accurate results. Google Cloud Data Flow, has a lot of these capabilities that they discussed in Millwheel baked in. We are working on similar stuff in Samza right now, but it's not there for public use yet. Next is, you need to be able to express your DAGs, as we call it, which is workflows. Like I said, multi-stage jobs, you need to be able to express that in an easy way, and the system should just stand up your multi-stage jobs. Storm has done a great job with it. There are other systems which also have support for it. I'm not sure what I touched. Lastly, you need a high-level DSL. Like Hive did had a great impact on the Hadoop community. Similarly, we need SQL support for stream processing, right? Azure Stream Insight has done a pretty good job at it. With this, stream processing and real-time processing becomes much more approachable for everyone. With that, great. So we have gone through all the hard part. Let me just quickly close. To close, let me just talk about why all this matters. Something's, okay, are we good? Yeah. With this onslaught of big data, LinkedIn has a similar problem. We do around 1.3 trillion messages per day get ingested into Kafka. Now, Kafka gets used for practically everything at LinkedIn, so this is not just like user data and such. Every message gets consumed 4 to 5 times, and we can have peaks of a couple million messages per second in terms of processing. Same thing with database change capture, operate at a very high scale there. We have Samza jobs in production, which do up to 1 million messages per second. And that's why all of this matters. Great. Thank you so much. These are some references. Hope you have a really good rest of the day.
Questions, please? Kartik, the infrastructure that you are using for all this, how much of it is on-premise, your own data centers? How much is using PAS? I don't know, how are you using AWS?
So at LinkedIn, we have our own infrastructure. So all of this is kind of deployed onto our own kind of machines and such. In essence, each of these systems, like Kafka, Databus, Samza, we operate these as PaaS. So we have an internal PaaS in LinkedIn, if you think about it. Yeah.
So once you invest in your own infrastructure, there's no way back? So that you're not like...
I'm sorry,
once you invest in your own PaaS, there's no way back. The scale makes you go further.
Yeah, that's always an interesting question, is that, yeah, if you have this is true with PaaS in general. Once you kind of start using, let's say, some part of AWS, let's say you use Kinesis or Redshift or whatever, you are kind of tied to that PaaS architecture because you're not going to change your apps very frequently, right? So if you really want to move between cloud platforms, let's say you want to move from AWS to Azure to Google Cloud or whatever, if you're running mostly just compute, right? So if your only dependency is on compute and then you operate like systems like we are operating, then you can take the systems, run it in the public cloud, except that the only thing that you leverage in the public cloud is compute. You don't leverage PaaS, right? Which is kind of pros and cons, I guess, because managing your own systems is hard, right?
Definitely. Yeah. Very good. Fantastic. Thank you very much, Kartik.
Thanks.